So to avoid these problems of complementary signals of phi and phi bar, what we come up to a concept is nothing but use of a dual non-overlapping clocks. Means you will use a clock phi 1 and phi 2 and ensure that both of them non-overlap or not overlap with each other. Let's understand this. Suppose this was my T. What I have done is I have reduced my phi. Suppose my phi was going high for a larger time initially, correct? Now what I have done is I have made my phi high for a small time. I have made my other signal high also for a small time, and the remaining time which I could save, I used it for making both of them non-overlapping. What you need to understand, if you look at the diagram clearly, initially we wanted phi and phi bar to be 0, right? Which means both of them were exactly complementary, but we saw the problems of chart leakage, clock skew, and also the problems like race condition. So what I've done is I made my phi 1 and phi 2 ending with 0, means no part of them overlaps with each other. Look at it properly. When this is high, this is low. When this is high, this is low. I've considered finite rise time, finite fall time also. What I have done is I've reduced my width of phi 1 and phi 2 compared to what I had initially, and I made some part of that to be non-overlapping, or I get some room for my rise time and my fall time. The only drawback what I did here is I reduced the time of my phi to be high, or I reduced my time for my phi bar to be high. If I have to compare with the previous case, now it's phi 1 and phi 2, and when I reduce that time for the computation for my logic block is slightly reduced, but I ensure that there will be no problem in the functionality because both of them are completely non-overlapping to each other. So this is nothing but the condition is achieved. Phi 1 dot phi 2 is equal to 0, dual non-overlapping clock. Similarly, we can go ahead and have triple non-overlapping clocks like this, where you have phi 1, phi 2, phi 3, ending of all three is equal to 0, means no part of it would overlap. Similarly, we can go ahead and do different styles as well. Let's go ahead and see. We already saw static circuits cascaded. Here I have cascaded a dynamic circuit, a NORA circuit, which I have covered in details in one of the clips. So I'm not getting into the details of its working. What I only want you to understand here is when phi is equal to 0, phi bar is equal to 1, this is on, this is on. There will be a capacitor here, so this will get charged. This is off, right? And this is also off, so no part to ground. This will charge, capacitor here, this will discharge. Correct? When phi goes to 1, this turns on. That means phi bar is 0, so this turns on. And now it's nothing but part to ground, input A, output going here. This is on, correct? So I'm not drawing that. This is my PMOS. This is my another PMOS. And this is off. So this is how the connection is towards VDD. And this is the connection towards ground. So let's say if A was 1, that means this node would go to 0, which will go as an input to this guy. So this turns on. So let's presume that this is also 0. So this is also on. So output will go to VDD. So this is a dynamic logic cascade which I have shown, or NORA circuit which I have shown here. But what happens here is this all happens when phi is equal to 1, and after this guy computes, this guy can start its computation. So when phi becomes 1, it is nothing but the evaluate phase, and in evaluation phase, evaluation happens sequentially. First this, then this, if there is another cascade, then that, then that. So everything is happening one after the another, which means if first guy is taking 2 nanoseconds, the next guy will start after 2 nanoseconds. If it takes 3 nanoseconds, after 5 nanoseconds, the third guy will start. And it's a rippling effect, sequential, one after the other. It will lead to a lot of delay. So to avoid this problem, we need parallel execution, which is nothing but pipeline systems. Pipeline systems, all these blocks can work parallelly. It can improve the throughput of your system, the rate at which the output is produced. I hope you have followed this. Stay tuned for further clips, and thank you very much.